Okay. In last lecture, we have completed what is a linear Diophantine equation and some theorems depending on linear Diophantine equation. That is, the theorem is nothing but if ax plus by equal to c is any linear Diophantine equation, then it has a solution if and only if d divides c, where d is nothing but the GCD of that two integers ab, and if d divides c, then the given linear Diophantine equation of the type ax plus by has a solution. And after that, we have seen one more theorem in which we have first proved a linear Diophantine equation ax plus by equal to c has a solution if and only if d divides c, where d is the GCD of AB. And after that, we have seen if x naught y naught be any particular solution of given linear Diophantine equation ax plus by equal to c, and after that we have find out all the solutions of the given linear Diophantine equation, and they are of the type x dash equal to x naught plus b upon d into t, and y dash equal to y naught minus a upon d into t, where d is any arbitrary integer. Therefore, if we replace t by minus t, then we get the corresponding values of x dash and y dash. And after that, we have seen two corollary depending on this theorem. For that, we have taken GCD of AB is equal to 1, and from this one we have find out the values of x dash and y dash, and which are nothing but x dash equal to x naught plus b into d, sorry, b into t, and y dash equal to y naught minus a into t, and similar by replacing t by minus t. Now, and today we have to start, sorry, we have to see how to how to check how to check the given linear Diophantine equation has a solution or not. Let us consider first one. 12x plus 18y will be equal to 30, and now we have to compare this equation with our linear Diophantine equation of the type ax plus by equal to c. Now let us compare it with ax plus by equal to c. So from this one, a is nothing but 12, b is nothing but 18, and c is nothing but 30. Now, in previous lecture, we have already proved that a linear Diophantine equation of the type ax plus by equal to c has a solution if and only if d divides c, where d is nothing but GCD of AB. So for that, we have to find out the GCD of two integers AB, and which is nothing but the value d. So GCD of AB, as here 12 is nothing but a and b is nothing but 18, therefore GCD of 12 comma 18. Now according to Euclid's theorem, GCD of 12 comma 18 is nothing but 6. Now here we get the value of d. Now it remains to check whether this d divides c, that is whether 6 divides 30. As 6 divides 30, then by that theorem the given linear Diophantine equation has a solution. Okay. Now, similarly, we have to check for 2x plus 3y equal to 4. Now, again, we have to compare this one with ax plus by equal to c. And from this, a is nothing but 2, b equal to 3, and c equal to 4. And as 2 and 3 are relatively prime integers, therefore GCD of 2 and 3 is nothing but 1, and which is nothing but d. And as 1 is a divisor of every positive integer, therefore 1 divides 4. Again, as 1 divides 4, therefore the given linear Diophantine equation 2x plus 3y equal to 4 has a solution. Now let us check for the third one, that is 6x plus 51y is equal to 22. Now again we have to compare this one with ax plus by equal to c, and which is the our original linear Diophantine equation. Therefore from this one, a is nothing but 6, b is equal to 51, and c is nothing but 22. Now if we find out the GCD of 6 and 51, then GCD of 6 and 51 is nothing but 3. Okay. Therefore, GCD of 6 comma 51 will be equal to 3, and 3 does not divide 22. And we know that the linear Diophantine equation ax plus by equal to c has a solution if and only if d divides c. That is, as the given statement is if and only if, therefore if 3 does not, as 3 does not divide 22, therefore from this one we conclude that the given linear Diophantine equation has a no solution, which is from that statement, that is linear Diophantine equation ax plus by equal to c has a solution if and only if d divides c, as d does not divide c, which implies linear Diophantine equation has a no solution. That is if p implies and implied by q, which implies p implies q and q implies p. Okay, as p implies q and negation of q implies negation of p, as here d does not divide c, which implies the linear Diophantine equation has a no solution. Okay, now similarly we have to check for the these are the examples depending on this theorem. Okay, Now find all the solutions of linear Diophantine equation 172x plus 20y is equal to 1000 and check whether the solution is positive or not. Here first we have to see whether the given linear Diophantine equation has a solution or not, and if it has a solution then we have to find out all the solution of that linear Diophantine equation, that is 172x plus 20y will be equal to 1000. Okay, and after that we have to check whether the solution is positive or not. So first here let us check whether the given linear Diophantine equation has a solution or not. For that we have to compare this one with ax plus by equal to c, and if we compare then value of a is nothing but 172. Similarly b and c are nothing but 20 and 1000. So now here we have to find out the GCD of 172 and 20, since a is nothing but 172 and b is nothing but 20. Therefore by using Euclid's lemma, that is this one, 172 is nothing but 20 into 8 plus 12. Now we have to express 20 as a multiple of 12 into multiple of 12 plus something remainder, that is 20 is nothing but 12 into 1 plus 8, and 12 is nothing but 8 into 1 plus 4, and 8 is equal to 4 into 2, and which is equal to 8 plus remainder is nothing but 0, as this one is the Rn, therefore 4 is nothing but the GCD. Therefore GCD of 172 comma 20 is nothing but 4. Now we have to check whether this 4 divides 1000 or not, but we know that 4 divides 1000. Therefore as 4 divides 1000, therefore according to that statement the linear Diophantine equation has a solution. Now we have to express the GCD4 as a linear combination of these values of a and b, that is 172 and 20. Okay, now from this one, this Euclid's theorem, 4 is nothing but 12 minus 8 into 1. So if we put 4 is equal to 12 minus 8 into 1, then we get the value of 8 from this second step. Then we have to put value of 8, and after that we have to put the value of 12. So let us take 4 is equal to 12 minus 8 into 1. 12 minus 8 is nothing but 20 minus 12 into 1. So which is nothing but 12 minus of 20 minus 20 minus of minus plus 12. Therefore 12 plus 12 is nothing but 2 times 12 minus 20. Now we have to put the value of 12, which is from the Euclid's algorithm, and 2 into the value of 12 is nothing but 172. 172 minus 20 into 8. Now we have to put this one in this step, that is 172 minus 12 into 8 minus of 20, and which is nothing but 2 times 172 minus 8 into 2 16, 16 times 20 minus of 20 as it is, which is nothing but 2 into 172 minus of 17 into, that is minus 16 plus minus 1, which is nothing but minus of 17 into 20. Now let us multiply both sides by 250. Then we get LHS is nothing but 1000, and which is equal to 2 into 250 is nothing but 500 into 172 minus of 17 into 250 is 4250 into 20. Now if we compare this one, let us take the value, this 500 is nothing but x naught, and minus of 4250 is nothing but y naught. Therefore here x naught is 500 and y naught is nothing but minus of 4250. Now we know that again, if x naught and y naught are the particular solutions of the given linear Diophantine equation, then x dash is nothing but x naught plus b upon d into t, and y dash is nothing but y naught minus a upon d into t. Therefore x dash is nothing but x naught is 500 plus b is here 20 divided by d. D is the GCD. GCD is 4 into t. 20 divided by 4 is nothing but 5. Therefore x dash is nothing but 500 plus 5t. Similarly y dash is nothing but y naught minus a upon d into t. Therefore, and here we get the value of y naught, and which is nothing but minus of 4250 minus of a is nothing but 172 divided by 4 into t. 172 divided by 4 is nothing but 43. Therefore y dash is nothing but minus of 4250 minus 43 into t. So here we have find out the values of x dash and y dash, that is all the solutions of the given linear Diophantine equation, and which are nothing but x dash and y dash. If we run the value of t, then we get one solution for each value of t. Therefore x dash and y dash are the remaining solutions of the given linear Diophantine equation. Therefore first two steps here we have solved. Now we have to check whether this solution is a positive or not. For positive, let us consider x dash and y dash. That is, we have to check whether x dash and y dash are positive or not. Okay, therefore, let us consider x dash is greater than 0, but x dash is nothing but 500 plus 5t. Therefore, from this one, 5t is greater than minus of 500. That is, we have to subtract minus 500 from both sides. Therefore, 5t is greater than minus of 500. From this one, if we divide both sides by 5, then we get t is greater than minus of 100. And similarly, we have to consider y dash is also greater than 0. But y dash is nothing but minus of 4250 minus of 43t, and which is greater than 0. If we multiply both sides by minus 1, then this inequality will be changes. That is, 4250 plus 43t is less than 0. From this one, 43t is less than minus of 4250, and from this one, next step is nothing but t is less than minus of 98.83. Therefore, from as t is greater than minus 100 and t is less than minus of 98, then t lies between these two value, that is minus 100 to minus of 98, minus of 98.83. But we know that there is only one integer value in between these two, and which is minus of 99. Therefore, value of t is nothing but minus of 99. Now we have to put this value t equal to minus 99 in x dash and y dash. X dash is nothing but 500 plus 5t, and y dash is nothing but minus of 43t. Therefore, after putting t equal to minus 99, we get x dash is nothing but 500 plus 5 into minus 99, which is nothing but 500 minus 495, which is equal to 5. And y dash is nothing but minus of 4250 minus 43 into minus 9, and which is nothing but minus of 4250 plus 4257. Minus 4250 plus 4257 is nothing but 7. Therefore, here we get the value of x dash is as 5 and y dash is 7, and both are positive. Therefore, the given linear Diophantine equation has a solution, and the solution is positive. Similarly, we can solve for any example. Let us consider second one. Find all the solutions of linear Diophantine equation 56x plus 72y is equal to 40, and check whether the solution is positive or not. Let us consider the given linear Diophantine equation, and which is 56x plus 72y, which is equal to 40. Now we have to compare this one with ax plus by equal to c, and from this we have to find out the values of a, b and c. And a is nothing but 56, b is equal to 72, and c is equal to 40. Now we have to find out, that is, if we have to check whether this linear Diophantine equation 56x plus 72y is equal to 40 has a solution or not, then we have to find out the GCD of these two integers 56 and 72. And GCD of 56 and 72 is nothing but 8. That is from the Euclid's theorem, that is 72 can be expressed as 56 into 1 plus 16, which from this one 56 is nothing but 16 into 3, which is 48, plus 8 is equal to 56. Now we have to express 16 as a multiple of 8. Therefore, 16 is nothing but 8 into 2 plus 0. Therefore, GCD is nothing but 8. That is Rn minus 1 is the GCD. And now here we have find out the GCD of two integers 56 and 72. Now we have to check whether the GCD divides 40 or not. As 8 divides 40, therefore from the previous theorem, the given linear Diophantine equation has a solution. Therefore, here we have checked whether the linear Diophantine equation has a solution or not. But now we have to find out all the solutions of the given linear Diophantine equation, and for that we have to express the GCD as a linear combination of these two integers a and b, and which are nothing but 56 and 72. Therefore, as we have backtracing these steps, then we get 8 is nothing but 56 minus 16 into 3, and 16 is not, value of 16 is nothing but 72 minus 56 into 1. Therefore, 8 is nothing but 56 minus 16 into 3, and 16 is nothing but 72 minus 56 into 1. Therefore, 56 minus 72 into 3 minus of minus plus 56 into 3. Therefore, 3 times 56 plus 1 times 56, which is nothing but 4 times 56 minus of 3 times 72. Therefore, we get 8 equal to 4 times 56 minus plus minus of 3 times 72. Now we have to multiply both sides by 5. Then we get LHS as a 40, that is value of C. Therefore 40 is equal to 4 into 5 20 into 56 minus 3 into 5 minus of 15 into 72. Now from this one, value of x naught is nothing but 20 and value of y naught is nothing but minus of 15. Therefore here we get the particular values of given particular solutions of a given linear Diophantine equation, and which are 20 and minus 15. Now we have to put this one in x dash equal to x naught plus b upon d into t, and y dash is equal to y naught minus a upon d into t. Let us first find out the value of x dash. X naught is equal to 20 plus b is nothing but 72 divided by d is the GCD, and which is 8 into t. 20 plus 72 divided by 8, 9 into t. And similarly y dash is nothing but y naught is minus 15 minus of a is 56 divided by its GCD of ab, which is 8 into t, minus of 50 minus 7t. Therefore here we get the values of x dash and y dash, and which are nothing but 20 plus 90, and y dash is nothing but minus of 15 minus 7 into t. Now therefore as the given linear Diophantine equation has a solution, therefore for each value of t we get one solution. Therefore there are infinite number of solutions for the given linear Diophantine equation, that is for one for each value of a t, where t is a t belonging to set of integer. Therefore now it remains to check whether the given solution is a positive or not, and for that we have to check whether x dash and y dash are greater than 0 or not. Let us consider x dash is greater than 0, but x dash is nothing but 20 plus 90. Therefore 20 plus 90 is greater than 0, and from this one 90 is greater than minus 20, and from this one t is greater than minus of 20 divided by 9. And similarly for y dash, as consider y dash is greater than 0, which implies minus of 15 minus 70 is greater than 0. If we multiply minus 1 from both sides, then the inequality reverses. Therefore 15 plus 70 is less than 0. 70 is less than minus of 15. From this one t is less than minus of 15 divided by 7. Therefore the value of t lies between minus of 20 divided by 9 to minus of 15 divided by 7, and which is nothing but minus of 20 divided by 9 is nothing but minus of 2.22, and minus of 15 divided by 7 is nothing but minus of 2.14. Now here t lies between minus 2.22 to minus 2.14, and we know that t is any arbitrary integer, but here we get the decimal terms. Therefore in between these two terms, minus of 2.22 minus of 2.14, there is no integer. As there is no integer from in between these two values, therefore we have to take the nearest integer among these two values, and we know that the nearest integer to minus 2.22 and minus 2.14 is nothing but minus of 2. Therefore value of t is nothing but minus 2. Here we take the value of t as minus 2, since we know that t is an integer, and here t is lies between minus 2.22 to minus 2.14, but there is no integer value in between these two terms. Therefore we have to take the value of t as a nearest integer, and which is nothing but minus 2. Therefore t is nothing but minus 2. Put t equal to minus 2 in x dash and y dash. Therefore we get x dash is equal to 20 plus 90. T is nothing but minus 2. 20 minus 18 is nothing but 2. Therefore we get the value of x dash is 2, but y dash is equal to minus of 15 minus 7 into t, and t is minus 2. Minus 15 plus 14, which is equal to minus 1. But here we get the value of x dash is positive, but y dash is not positive. Therefore the given linear Diophantine equation has no positive solution, since y dash is less than 0. Now here we have choose t as a minus 2. If we take t equal to minus 3, then also we get among these two x dash and y dash, one of them is negative. That is, if we take t equal to minus 3, then 20 plus 9 into minus 3. Minus 3 into 9 is nothing but minus of 27. 20 minus 27 is nothing but minus 7. And here we get the positive, that is minus of 15 minus of 7 into minus 3. Minus 3 into 7 minus of 21. Minus 21 into minus 1, which is nothing but plus 21. Minus 15 plus 21 is nothing but 6. But here if we put t equal to minus 3, then we get the value of y dash is positive, but value of x dash is negative. Therefore if we take any integer value nearest to these terms, then we get at least one among these two x dash and y dash is negative. Therefore the given linear Diophantine equation has a no positive solution. Okay. Now similarly, we have to solve this one, whether this linear Diophantine equation has a solution, and if it has a solution, then we have to find out all the solutions of this linear Diophantine equation. Okay. Therefore, again we have to compare this one with the Diophantine equation ax plus by equal to c, and from this one a is nothing but 24, b is equal to 138, and c is equal to 18. Again we have to express 138 as a multiple of 24 into multiple of 24 plus something remainder, and which is nothing but 24 into 5 plus 18, that is 24 into 5 is 120 plus 18, which is 138. Now we have to express 24 as a 18 into 1 plus 6, and 18 is nothing but 6 into 3 plus 0, and from this one the GCD of 24, 138 is nothing but 6, and 6 divides c, that is c equal to 18. Therefore the given linear Diophantine equation has a solution. Now again we have to practice in the steps of Euclid's algorithm, that is 6 is equal to 24 minus 18 into 1, that is from the second step, and value of 18 is nothing but 138 minus 24 into 5. Therefore 24 minus 138 minus of 24 into 5, which is equal to 24 minus of 138 minus of minus plus 5 times 24. 5 times 24 plus 1 time 24, which is 6 times 24 minus of 1 times 138. Therefore from this one we get the as here c is equal to 18, therefore we have to multiply both sides by 3. We get 18 is equal to 6 into 3 18, and minus 1 into 3 minus of 3 into 138. Therefore we get the values of x0 and y0, and which are the particular solutions of the given linear Diophantine equation. Therefore x0 is nothing but 18 and y0 is nothing but minus 3, and from these values of x0 and y0 we know that how to find out all the possible solutions of the given linear Diophantine equation, and they are nothing but x dash is equal to x0 plus b upon d into t, and y dash is equal to y0 minus a upon d into t, where d is the GCD of two integers a and b. x0 is equal to 18 plus b is nothing but 138 divided by its GCD of two integers a and b, that is 6 into t, which is equal to 18 plus 23 into t, and y dash is equal to y0 minus a upon d into t. Okay, therefore y0 is nothing but minus of 3 minus a is nothing but 24 divided by 6 into t, which is equal to minus 3 minus 40. Therefore here we get the values of x dash and y dash. Actually in example 3, here we have to find out only all the solutions of the linear Diophantine equation, that is we have to find out up to x dash, up to values of x dash and y dash. If we have to check whether it has a positive solution or not, we can check. That is, let us consider x dash is greater than 0, but x dash is nothing but 18 plus 23t. 23t is greater than minus 18, t is greater than minus of 18 divided by 23. Similarly, for this y dash greater than 0, t is less than minus of 3 by 4. Therefore t lies between minus of 18 divided by 23 to minus 3 divided by 4, that is minus of 0.78 to minus of 0.75. Therefore from this one, as t lies between these two values minus 0.78 to minus 0.75, therefore value of t is nothing but minus of 0.76. But we know that t is an integer. As t is an integer, therefore minus of 0.76 is not possible. Therefore for this we have to take the nearest integer of this term, and minus 1 is the nearest integer of this term. Therefore take t equal to minus 1, and we have to put this value in x dash and y dash. Therefore x dash is nothing but 18 minus 23, and which is equal to minus of 5, and y dash is equal to minus of 3 plus 4, and which is 1. Therefore as here x dash is not greater than 0, therefore the given linear Diophantine equation has a no positive solution. If anyone have doubt, then please ask the questions, otherwise we will continue.
No, sir. No, sir.
Okay.
सर 1 घेता येत नाही का सर? ते पण एव्हरेस्ट आहे.
काय म्हणला?
1 घेता येत नाही का सर? नियरेस्ट आहे ते पण इंटिजर.
नाही, टीच्या जवळचा सगळ्यात जवळचा इंटिजर व्हॅल्यू घ्यायची आपल्याला. म्हणजे तुम्ही टीची व्हॅल्यू कुठून कुठपर्यंत आहे, मायनस 0.78 ते मायनस 0.75, म्हणजे याच्या जवळ सगळ्यात पॉसिबल दोन व्हॅल्यू येतील. कोणते कोणते? 0 आणखी -1, हे दोन त्याच्या जवळचे इंटिजर आहेत. जर तुम्ही -1 सगळ्यात जवळचं असेल, कारण हे 0.5च्या पण -0.5च्या पुढे आहे. -1च्या ऐवजी जर तुम्ही 0 जरी घेतलात तरी बघा, जर 0 घेतलात व्हॅल्यू, आणखी एक्स डॅश मध्ये जर 0 पुट केला तर हा +18 भेटेल, पण वाय डॅश मात्र तुम्हाला -3 भेटेल. म्हणजे दोन्हीपैकी कोणता तरी एक तुम्हाला निगेटिव्ह भेटेलच. दोनच पॉसिबल व्हॅल्यू आहेत. सगळ्यात जवळची -1 आहे. -1 ऐवजी जर तुम्ही 0 जरी घेतलात तरी ते येणार नाही. ठीक आहे.
हो सर.
Now the next concept is primes and their distribution. Let us see one theorem. The smallest divisor other than 1 of any composite number is a prime. That is, here we have to prove that if we take any composite number, then its smallest divisor other than 1 is a prime number. Okay, let us see its proof. Let A be any composite number. As A is composite number, then it has at least one divisor D other than 1 and A, which is from the definition of composite number. Since any number is said to be a composite number if it has at least one divisor other than 1 and that element itself. Since if the number has only two positive divisors, that is 1 and the element itself, then the element is prime number. But here as given that A is a composite number, then it has at least one divisor D other than 1 and A. Okay, let us consider A has smallest divisor D, which is less than A. As D, here we have to consider D is the smallest divisor of element A. Okay, now as D is the smallest divisor of A, then we have to prove that this D is a prime number. Since here we have to prove that is the statement is nothing but the smallest divisor of a composite number is prime. That is, if we consider D is the smallest divisor, then D must be prime. If possible, suppose that D is a composite number. If D is a composite number, again from the definition of composite number, this D has at least one divisor, something D1, which is other than 1 and D. That is, D1 is the another divisor of D other than 1 and D. Therefore, D1 must be less than D, since D1 is not equal to D, and D1 is greater than D. Therefore, D1 is less than D. As D1 is less than D and D1 divides D and D divides A, then from the transitive property, D1 must divide A. Therefore, here we get one element D1 which divides A and which is less than D. Therefore, D1 is the smaller element than D. But we have already assumed that D is the smallest element. As D is the smallest element, then this one is the contradiction to our assumption, since D1 is less than D. And this contradiction arises due to our wrong assumption, that is D is a composite number. Hence, if we consider D is the smallest divisor, then D must be a composite number. Since if we take D is a composite number, then we get a contradiction. Hence, D must be a prime number. And from this, we say that the smallest divisor of any composite number other than 1 is always a prime integer. Okay, now next one is, if P is prime and A is any integer, then either GCD of A and P is equal to 1 or A is a multiple of P. Okay, given that P is a prime number and A is any arbitrary integer. As P is a prime number, then from the definition of prime number, P has at most two positive divisors, that is 1 and P. Therefore, if suppose GCD of AP equal to 1, that is, from this one we say that if P is a prime number, then it has only two positive divisors, 1 and P. Therefore, GCD of AP equal to 1 or GCD of AP equal to P. These are the only two possibilities for GCD of P with any integers. Okay. Now, A possible, suppose that GCD of AP is equal to 1, then the theorem is proved. That is, if P is a prime number and A is any arbitrary integer, then we have to prove that GCD of AP equal to 1 or A is multiple of P. If here we get GCD of AP equal to 1, then the theorem is already proved. There, if possible, suppose that GCD of AP is not equal to 1, then GCD of AP is not equal to 1, then which implies GCD of AP is equal to P. GCD of AP is equal to P is possible only if this A is equal to P or A is a multiple of P. That is, if A equal to P, then also we say that A is a multiple of P, since A is 1 times multiple of P, or GCD of AP equal to P is possible only when A is a multiple of P. Therefore, from this one we conclude that if P is a prime number and A is any integer, then either GCD of AP equal to 1 or A is a multiple of P, which is from this statement, that is, if P is a prime number, then it has only two divisors, 1 and P. Therefore, the possible values of GCD of P with any integers are only two possibilities, that is either GCD is 1 or P. If GCD is 1, then our theorem is already proved. Therefore, and if possible, suppose that GCD is not equal to 1, then GCD must be equal to P. And if GCD equal to P, then the value of A must be a multiple of P. Therefore, the given statement will be proved. Now, if P is a prime number and P divides AB, then either P divides A or P divides B. That is, actually it is somewhat similar to our Euclid's theorem. That is, P is a prime number. That is, A divides BC and GCD of AB will be equal to 1. Then A must divide C. But here, given that P is a prime number and P divides AB, and we have to prove that P divides A or P divides B. Okay, let us consider. Let's take the given, that is, P is a prime number and P divides AB. If possible, suppose that P divides A. If P divides A, then there is no need to go further. That is, here we have to prove that for given prime P and P divides AB, we have to prove that either P divides A or P divides B. If P divides A, then there is no need to go further. Okay, that is, in first step, we get the result. If possible, suppose that P does not divide C. As P does not divide C and P is a prime number, then GCD of integer A with P must be equal to 1. Okay, since P does not divide A, implies that A is not a multiple of P. And if possible, and if there is only one possibility, that whether A divides P or not. If A divides P for prime P, then A is either 1 or P. But as P does not divides A, therefore A is not equal to P. Then there is only one possibility of A equal to 1. If A equal to 1, then also GCD of AP will be equal to 1. Okay. Therefore, as P does not divide C, then GCD of A and P is 1. As GCD of two integers A and P is equal to 1, then there exist two integers X and Y such that the GCD 1 is nothing but AX plus second integer PY. Okay. Now multiply both sides by B. Then we get B is equal to A into BX plus P into BY. Okay. Now, in given statement, we have given that P divides AB and P divides PB always. Since here there is a term of P into B and P always divides P. Therefore, P divides P into B. As P divides AB and P divides PB, therefore P divides its any linear combination, which implies P divides AB into X plus PB into Y. So here there is a term B which is common in both the terms. Therefore, take common B, then it is nothing but P divides B into AX plus PY. But AX plus PY is nothing but 1. Therefore, P divides B into 1, that is P divides B. So here, the given statement will be always true. That is, if P is a prime number and P divides AB, then either P divides A or P divides B. In first case, we have to take P divides A. If P divides A, then there is no need to go further. And if possible, P does not divides A, then P must divides B. Okay. Now, corollary depending on this theorem, if P is a prime and P divides A1 into A2 into up to so on AN, that is product of these n integers, then P must divides at least one AK among these K AKs, that is K lies between 1 to n. Okay. Now, given that P is a prime number and P divides A1 into A2 into up to so on AN, and we have to prove that P divides AK for some positive integer K, where K is nothing but that is K is lies between 1 to n. Okay, now we will prove this theorem by that is this corollary by using the mathematical induction on integer n, that is positive integer n. Let us consider for n equal to 1. If n is equal to 1, then there is only one possibility, that is A1, that is P divides A1. Then as here we have to prove that if P is a prime number and P divides A1 into up to so on AN, then P divides AK for at least 1 K. as there is only one n, therefore p divides a1, therefore the result will be obviously true. Now, in second one, let us consider n equal to 2. That is, there are two possibilities for n, that is 1 and 2, which implies p divides a1 into a2. But in above theorem, we have proved that if p divides ab and p is a prime number, then either p divides a or p divides b. Therefore, as here given that p is a prime number and p divides a1 into a2, then from previous theorem, p divides a1 or p divides a2. Therefore, the result is true for n equal to 2. Therefore, the result will be true for n equal to 1 and n equal to 2. Now we have to assume the result is true for some n equal to k minus 1. That is, this one is nothing but the inductive state. In that, we have to assume that the result will be true for some n equal to k minus 1. That is, if p divides a1 into a2 into up to so on ak minus 1, then p divides ak dash for some k dash lies between 1 to k minus 1. Since here k dash is lies between 1 to k minus 1. This one is the inductive step. In that, we have assumed the result will be true for n equal to k minus 1. Now, in last step, we have to prove that the result will be true for n equal to k. Let us consider p divides a1 into a2 into up to so on ak. Now, this a1 into a2 into up to so on ak is an integer. Therefore, p divides a1 into a2 into up to so on ak minus 1 into ak. This term a1 into a2 into up to so on ak minus 1, as a1 to a1 a2 up to so on ak minus 1 all are integers, then its product must be an integer. Therefore, this one will be considered as a one particular integer sum am. So a1 into a2 into up to so on ak minus 1 is nothing but am into ak. Again, we know that if p divides a into b, then p divides a or p divides b. As here p divides am into ak, then either p divides am, but am is nothing but a1 into a2 into up to so on ak minus 1, or p divides ak. Now, if possible, suppose that p divides ak, then the result will be whole. Since here we have to prove that if p divides a1 to ak, then we have to prove that p divides at least one ak, that is one am, that is am running from 1 to k. As here already we get p divides ak, then there is no need to go further. The result will be whole for that step only. Now, if suppose that p does not divide ak, then p must divides a1 a2 up to so on ak minus 1. And in inductive step, we have proved that if p divides a1 a2 up to so on ak minus 1, then p must divides ak dash for some k dash lies between 1 to k minus 1. Therefore, for both the possibilities, the result will be true. Hence, from this we say that the result will be true for n equal to k. From this one, from step 1, 2, 3 and 4, the result will be true for any positive value of n. Okay, that is, if p divides a1 a2 up to so on an, then p must divides ak for k lies between 1 to n. Now, if suppose these a1 a2 up to so on an are nothing but the prime numbers, that is, there is one corollary depending on this theorem. If p, q1 q2 up to so on qn are primes, in previous theorem we have proved that a1 a2 up to so on an are any arbitrary integer, but here we have to take this q1 q2 up to so on qn are primes, and p divides its product, that is product of these n integers q1 q2 up to so on qn. Then we have to prove that p is equal to qk for some integer k, where k lies between 1 to n. Here, given that p divides q1 into q2 into up to so on qn, and by previous corollary we know that p divides qk for some k lies between 1 to n, which is from the previous corollary or previous theorem, this one. That is, if p divides a1 a2 up to so on an, then p must divide some ak where k lies between 1 to n. As q1 q2 up to so on qn are also an integers, but here given that these are the primes, as they are primes, they must be integers. Therefore, from previous corollary, p must divide qk for some k lies between 1 to n. But we know that qk is a prime, qk is prime, and p is also an prime, and qk is divisible by this prime p. As qk is a prime, then only possible positive divisors of qk are 1 and qk only. But here we get one prime p which divides qk, then the possible value of p, possible value of p is nothing but 1 and qk only. Since p divides qk and qk is also a prime, then its only divisors are 1 and qk. Then the possibility for p is nothing but 1 and qk. But we know that p is also a prime. As p is a prime, then p must be not equal to 1. As p is not equal to 1, then p must be equal to qk. Therefore we must have p is equal to qk. And from this we conclude that if p and these n integers q1, q2 up to so on qn are primes, and p divides product of these n integers, then p must be equal to qk for some integer k, where k lies between 1 to n. Okay. Now, if anyone have a doubt, then please ask the questions.
सर ते निगेटिव्ह इंटिजर साठी प्रूव्ह होत नाही ना? वरचं जे वरचं कोरोलरी सर, हे निगेटिव्ह इंटिजर साठी होत नाही ना? म्हणजे
का होत नाही? होईल ना, गरजेचं नाही ना तुमचे A1 A2 अप टू सो ऑन एन पॉझिटिव्ह इंटिजर्स असतील, निगेटिव्ह लाईन होईल.
हा,
पी प्राइम आहे, प्राइम जरी असेल तरी तो डिवायझर असेल ना निगेटिव्ह इंटिजरचा. फॉर एक्झाम्पल 2 इज डिवायझर ऑफ A1 A2 कोणतेही आर्बिट्ररी इंटिजर आहेत. तुम्ही -4 घ्या, 2 जर प्राइम पी असेल तर 2 हा 4 ला डिवाइड करेल आणि -4 दोन्हीलाही डिवाइड करेल ना.
हो सर.
म्हणजे A1 A2 तुमचे पॉझिटिव्ह असतील किंवा निगेटिव्ह असतील, रिस्ट्रिक्शन नाहीये त्यावर. हा, तेच जर या केसमध्ये जर तुम्ही गेलात तर इथे निगेटिव्ह असू शकत नाहीत ना, कारण प्राइम नंबर्स निगेटिव्ह नाहीये. जर तुम्ही Q1 Q2 अप टू सो ऑन Qn हे प्राइम जर घेतलात तर पॉसिबिलिटीज येत नाही की हे निगेटिव्ह असतील. Since prime numbers are the subsets of set of natural numbers and there is no natural number which is negative, therefore Q1 Q2 up to so on Qn must be a positive numbers.